Good morning all of you. Okay, in the last session have completed the types of stresses and analysis of stresses. Okay, in the fourth module of first unit, that is stresses in rigid pavement. Okay, in today's session I'll move on to some of the important definitions which is required, okay, in the Westergaard wheel load stress equations. Okay, some of about 4 important definitions you need to remember, okay, that is very beneficial for your semester end examination. Okay. Important definitions. Okay, there are 4 important terms. The first one, it is modulus of subgrade reaction K, and the second one, it is radius of relative stiffness, L, and third one, it is critical load positions, okay, and fourth one, it is equivalent radius of resisting section, B. Okay, these are the 4 important terms. Okay, the definition of these terms are very beneficial along with the theoretical formulas, okay, in the Westergaard wheel load stresses equations. Is it clear? And you may familiar with this modulus of subgrade reaction K, because in your highway engineering subject, okay, we have solved the numerical problems on modulus of subgrade reaction. Is it clear? Means with the help of plate load test results, you are going to obtain the modulus of subgrade reaction, no? Okay, I think you may all familiar with the modulus of subgrade reaction. Okay, even though I'll explain the definition of modulus of subgrade reaction and how you obtain the modulus of subgrade reaction. Okay, if you take the modulus of subgrade reaction K, we know that K is equal to P by delta. Means the modulus of subgrade reaction is inversely proportional to the displacement of the slab. Is it clear? Okay, here the modulus of subgrade reaction, okay, will be measured at a specified pressure level, okay, with the specified plate size. Okay, we all know that the modulus of subgrade reaction K is inversely proportional to displacement of the slab. Is it clear? Okay, usually the displacement level is measured at 0.125 centimeter. The displacement level is measured at 0.125 centimeter. Okay, see here, P divided by 0.125 centimeter is the displacement level. At this level, you are going to measure the pressure. Okay, then you will obtain this in terms of kg per centimeter square, because the pressure level you are going to measure in terms of kg per centimeter square, no, and okay, your displacement in centimeter, then it becomes the kg per centimeter cube. Okay, it is a unit of modulus of subgrade reaction. Okay, means if P is the pressure sustained, okay, by a rigid plate of diameter 75 centimeter at a displacement level of 0.125 centimeter, okay, that is in terms of kg per centimeter square. Is it clear? Means if P is the pressure sustained in kg per centimeter square by a rigid plate of diameter 75 centimeter, okay, at a displacement of 0.125 centimeter. Okay, then your modulus of subgrade reaction K is equal to P by 0.125 centimeter. Then we get it in terms of kg per centimeter cube. Now, if you want the definition of the modulus of subgrade reaction is very simple. Okay, the modulus of subgrade reaction K is the pressure sustained per unit deformation at specified pressure level or deformation level using specified plate size. That's it. Okay, what is modulus of subgrade reaction? It is very simple. Okay, it is the pressure sustained per unit deformation, okay, at a specified deformation level or pressure level, okay, using a specified plate size. Using a specified plate size, that is the modulus of subgrade reaction. Is it clear? Okay, this is regarding the first term, the modulus of subgrade reaction. Okay, next I'll move on to the second term, the radius of relative stiffness L. Okay, the Westergaard defined the radius of relative stiffness L is equal to EH cube divided by 12K 1 minus mu square whole to the power of 1 by 4. Westergaard defined the radius of relative stiffness L is equal to EH cube divided by 12K 1 minus mu square whole to the power of 1 by 4. Then what do you mean by this relative stiffness L? Okay, okay, in this the relative stiffness L we are going to measure in terms of centimeter. We are going to measure in terms of centimeter. Okay, next these terms E. Okay, where capital E is the modulus of elasticity of concrete in terms of kg per centimeter square. Modulus of elasticity of concrete in terms of kg per centimeter square, and H is the slab thickness in terms of centimeter. H is the slab thickness in terms of centimeter, and K we know that K is the modulus of subgrade reaction in terms of kg per centimeter cube. Kg per centimeter cube. Is it clear? Next, mu is the Poisson's ratio of concrete. Mu is the Poisson's ratio of concrete. If not given, okay, you may assume the Poisson's ratio of concrete is 0.15. You may assume the Poisson's ratio of concrete is 0.15. Okay, this is defined by Westergaard only. We all know that certain degree of resistance offered, okay, by a subgrade for the slab deflection. Is it clear? The subgrade will offer certain degree of resistance to slab deflection. Then the tendency of the slab to deflect, it's depend on the flexural strength of concrete. Is it clear? The tendency of the slab to deflect, that is depend on the flexural strength of concrete. Okay, the flexural strength in terms depends on, okay, slab thickness and the material properties. Okay, the relative stiffness of the slab with respect to subgrade support is dependent upon the properties of the slab and deformation characteristics of the subgrade material. Okay, this is with respect to the radius of relative stiffness L. Radius of relative stiffness L. Okay, sometimes in your competitive exams they may ask you to find the radius of relative stiffness L. Okay, for that they are given some of the datas like E, H, K and mu. Okay, sometimes they will give the value of mu or may not. Okay, you know that the value of mu, no, that is Poisson's ratio of concrete is 0.15. Okay, we can easily calculate if you know this formula in your competitive exam. Okay, next is critical load positions. Next is critical load position. Okay, you have completed modulus of reduction and relative stiffness. Next is critical load positions. Critical load positions, or we can say critical load locations. If you consider the pavement slab, okay, this is your interior loading, okay, this is interior, okay, this is the edge loading, edge, and this is the corner loading. This is the corner loading. Okay, you know that the pavement slab has the finite length and width. Okay, what is the finite length and width? That is measurable length and width. Okay, for the cement concrete slab, we have a measurable length and width. Okay, okay, because of that, the intensity of maximum stress induced by the application of given wheel loads, okay, is dependent on the position of the load acts on the pavement slab. Have understood? No? Means since your pavement slab has the finite length and width, okay, because of that, the intensity of maximum stress, okay, induced by the application of given wheel loads, okay, will be dependent on the position of the load acts on the pavement slab. Is it clear? Basically, okay, the load or the stress induced due to the corner loading, okay, will be a high amount. Means due to corner loading, there will be high amount of stress will be induced on the pavement slab. And due to interior loading, okay, there will be lower amount of stress will be acting on the pavement slab. Okay, where due to edge loading, it is moderate between the corner loading and interior loading. Moderate between corner loading and interior loading. Is it clear? Okay. Okay. The Westergaard identified 3 typical positions, that is interior, edge and corner loading, okay, with reference to the continuity of the slab, and those 3 positions are called critical load positions. Critical load positions. Okay. Usually for those 3 critical positions, they will give the number, like for the interior it is noted by I, and for the edge it is noted by small e, and for the corner loading they are noted by small c. I is the interior loading, E is the edge loading, C is the corner loading. Okay, you may observe in the figure, the interior loading is the one, okay, which is away from the edges and anywhere on the pavement slab. Okay, interior loading is the one which is away from all the edges of the pavement slab, which is away from all the edges of the pavement slab. Is it clear? Next, edge loading E is the one which is away from the corner, of the pavement slab. Okay, it is away from the corner of the pavement slab and anywhere on the edge, along the edge. Anywhere along the edge, but it should be away from the corner. That is the edge loading. And the corner loading, okay, the load induced by a wheel, the load induced by a vehicular wheel at the intersection of 2 edge portions. At the intersection of 2 edge portions, okay, that is called corner loading. Okay, here also you may get corner loading. Here also, because at these portions, okay, there are 2 edge portions are intersecting, no, okay, that is the corner loading. Okay, interior loading is the one, okay, which is away from all the edges of the pavement slab and acting anywhere on the pavement slab except from the edges. And edge loading is the one, okay, which is away from the corner of the slab and acting along the edges. And corner loading is the one which is acting, okay, at the intersection of two edge portions. At the intersection of two edge portions. Is it clear? Okay, this is regarding the critical load positions. Okay, that is the third one. Okay, the next one is equivalent radius of resisting section B. Equivalent radius of resisting section B. Equivalent radius of resisting section B. Okay, the Westergaard approximated the equivalent radius of resisting section B, okay, with the help of the radius of wheel load distribution A and the slab thickness H. Is it clear? Okay, the Westergaard approximated B, okay, with A and H. With A and H. Okay, usually you may have two relations for B. Okay, the first condition is number one, if A is less than 1.724H. If A is less than 1.724H, what is A? Radius of wheel load distribution and H is the slab thickness. Okay, in that case the B is, okay, root of 1.6 A square plus H square minus 0.675 H. Okay, the 1.6 A square plus H square is under root, okay, then minus 0.675 H. Okay, this is the relation you are going to use to know the value of B when A is less than 1.724 times of slab thickness. 1.724 times of slab thickness. Is it clear? And the second relation, if A, that is the radius of wheel load distribution, more than 1.724 times of slab thickness, okay, then your B is equal to A. B is equal to A. Okay, usually the B value you are going to obtain in terms of centimeter only, the equivalent radius of resisting section. Okay, means the Westergaard approximated the equivalent radius of resisting section, okay, with the wheel load distribution A and the slab thickness H. Okay, there will be two relations. Okay, the first one it is, if the radius of wheel load distribution A less than 1.724 times of slab thickness, then B is equal to root of 1.6 A square plus H square minus 0.675 H. Okay, if A is greater than 1.724 times of slab thickness, then your B is equal to A. Then the question is, when the matter of equivalent radius of resistance section arise, if you consider the interior loading, the maximum bending moment occurs at the loaded area and that will be acts radially in all directions. The bending moment will act radially in all directions. If the load concentrated on a smaller area of the pavement, okay, then the question is, to what sectional area, okay, your pavement is effective in resisting bending moment, that is the equivalent radius of resisting section B. Is it clear? Means with the load concentrated on smaller area, okay, then the question is, to what sectional area of the pavement, okay, is effective in resisting the bending moment. Okay, that is the equivalent radius of resisting section B. Okay, this is regarding the four important terms which is required in the Westergaard, okay, stress equations. First, I'll move on to the Westergaard wheel load stresses. Westergaard wheel load stresses. Okay, we know that the Westergaard identified the three critical positions with reference to the continuity of the slab, no, that is interior, edge and corner. Okay, those three typical positions are called critical load positions, no. SI, SE and SC, that is the maximum wheel load stress due to interior loading, maximum wheel load stress due to edge loading, maximum wheel load stress due to corner loading. SI, SE, SC. Okay, maximum stress due to interior loading, maximum stress due to corner loading, that is maximum wheel load stress due to edge loading, maximum wheel load stress due to corner loading. Okay, if you take the first one, number 1, wheel load stress SI due to interior loading. Okay, that is SI is equal to 0.316 P by H square, 0.316 P by H square into 4 log to the base of 10 L by B, okay, plus 1.069 plus 1.069, okay, in terms of kg per centimeter square, in terms of kg per centimeter square. Okay, SI is the wheel load stress due to interior loading, that you know that. Then 0.316 P by H square, where P is the wheel load in terms of kg, H is the slab thickness in terms of centimeter, and L we know that. Okay, just now we have discussed the small l is the radius of relative stiffness in terms of centimeter, and we have discussed B also. B is what? Equivalent radius of resisting section, equivalent radius of resisting section in terms of centimeter. Okay, then if you compute all the parameters, then you will obtain the maximum stress due to interior loading. Okay, if you want to the second one, wheel load stress SE due to edge loading, due to edge loading. Okay, this SC is equal to 0.572 P by H square 4 log to the base of 10 L by B plus 0.359. Okay, SC is equal to 0.572 P by H square multiplied by 4 log to the base of 10 L by B plus 0.359. Similarly, okay, P is the wheel load in terms of kg, S is the slab thickness in terms of centimeter, L is the radius of relative stiffness in terms of centimeter, B is the equivalent radius of resisting section in terms of centimeter. Okay, this also you obtain in terms of kg per centimeter square. Is it clear? Okay, the third one it is wheel load stress SC due to corner loading, due to corner loading. Is it clear? That is SC is equal to 3P divided by H square, 3P divided by H square multiplied by 1 minus A into root 2 divided by L, root 2 divided by L power 0.6, power 0.6. SC is the wheel load stress due to corner loading, P is the wheel load in terms of kg, H is the slab thickness in terms of centimeter, A is the wheel load distribution in terms of centimeter, and we know that L is the radius of relative stiffness, radius of relative stiffness. Okay, these are the Westergaard's wheel load stress equations, Westergaard wheel load stress equations. Okay, the first one is the wheel load stress due to interior loading, second one is the wheel load stress due to edge loading, third one is the wheel load stress due to corner loading, that is SI, SE and SC. And the SE and SC, that is wheel load stress due to edge loading and wheel load stress due to corner loading, okay, of the Westergaards will be modified. Okay, those are called modified Westergaard equations. Those are called modified Westergaard equations. Okay, these are simply called Westergaard equations, but the SE and SC, okay, the maximum wheel load stress due to edge loading and maximum wheel load due to corner loading, okay, will be modified. Okay, those are called modified Westergaard's equations, modified Westergaard's equations, okay, for the wheel load stresses. Okay, and remember that only the modified equations is for edge loading and corner loading, but for the interior loading, okay, it will be remain the same. Then what is that modified Westergaard equation for edge loading and corner loading? Okay, that I have discussed here. Modified Westergaard's wheel load stress. Okay, the first one it is edge load stress by Teller and Sutherland, by Teller and Sutherland, means the Westergaard's edge load wheel load stress, edge load stress will be modified by Teller and Sutherland. Westergaard's edge stress is modified the Teller and Sutherland. That modified equation is SE is equal to 0.529 P by H square, 0.529 P by H square multiplied by 1 plus 0.54 mu, 1 plus 0.54 mu, which in turn multiplied by, this is 4 log to the base of 10 L by B plus log to the base of 10 B minus 0.4048, 0.4048. Okay, this is also get in terms of kg per centimeter square. Okay, you can refer the Westergaard equations due to edge loading, that is 0.572 P by H square, which is multiplied by 4 log 10 to the base of 4 log to the base of 10 L by B plus 0.359. Okay, and the modified Westergaard equation for edge loading, it is 0.529 P by H square multiplied by 1 plus 0.54 mu. Mu, you know that. What is that? It is the Poisson's ratio of concrete. It is 0.15, and which in turn multiplied by 4 log to the base of 10 L by B plus log to the base of 10 B minus 0.4048. Okay, these are modified Westergaard equations, okay, for edge loading. Okay, similarly, okay, corner load stress by Kelly, Kelly. Means the whatever the corner load stress is there, okay, which is given by Westergaard, this corner load stress is modified by a Kelly. Okay, very minute changes for Westergaard's and the modified Westergaard's corner load stress equation. Okay, small changes. What is that? Instead of this 0.6, it is 1.2. Instead of this power 0.6, it is 1.2. That's it. It is a small changes in corner loading. Okay, it is SC is equal to 3P by H square, okay, multiplied by 1 minus A into root 2 divided by L, okay, this is power 1.2, okay, this is also obtained in kg per centimeter square, okay, this is the modified corner load stress equation, that is Westergaard's modified corner load stress equation. Okay, okay, this is regarding the wheel load stresses. Okay.